Again, I am a quick reintroduction, Gary Kevorkian from Cisco, the host of today's event. Glad you're all able to join us again. Hope you had a chance to take advantage of our little morning break. We are going to restart with 3 sessions for the middle part of our day. We're going to kick off with Carlos and Cesar from BBVA Bank in Spain. They are return presenters. They were with us for the first time we did ScaleX back in November. And the focus of their talk is BBVA's journey to cloud native and the trials and tribulations of taking a major bank and all the finance and security issues that go along with it and going cloud native. So Cesar, Carlos, thank you again for joining us, and I will turn the WebEx over to you.
Great, thank you, Gary. Thanks a lot. Hi, my name is Cesar Martinez. I'm Senior Expert Architect in BBVA, and will be my colleague Carlos Diez, who is the Head of Container Platform. In this session, we are going to explain our journey to transform our monolithic architecture to a microservice one. To do it, we'll start with a brief introduction of the company and some aspects of the architecture. We'll explain the microservices layers we implemented and the infrastructure used to do it, the changes we were facing on, and finally, we'll leave some time for questions. So let's start. Well, BBVA is a global finance service group having presence in more than 30 countries all over the world. We are more than 123,000 employees, and we have almost 80 million customers. BBVA is really focusing in technology and is investing a lot of resources to this area. So one of the reasons is to cover the tremendous growth of the digital interactions we have with our customers, challenging our technological solution constantly. And as you can see in the slide, the figures, it's showing us the growth we had in the previous years. Another good example, it's the recognition from Forrester Research that in 2019 chose us our app as the best bank application on the world for the 3rd year in succession. As the consumption of the technology is not constant during the year because of the marketing campaigns or how the customers schedule the use of our financial services, we have to handle with burst traffic, and the way to do it is using a hybrid cloud strategy. So apart from having this capacity to grow faster, the public cloud offers us the reliability and the options to offer some kind of active solutions. So as you can see in the map, we have two main regions. Apart from the hubs, one is in America and the other is in Europe, to allocate our services not only on-prem, but in the public cloud, and making the most of the benefits we both in both deployments. Back 5-6 years ago, we had the challenge of transforming the bank. We had the purpose of creating a new ecosystem that could support the big demand of these digital services for the bank that we were mentioning. We evaluated 2 options. The one was evolving the legacy models, or the one that we finally chose, starting from scratch, a new generation model, and moving these workloads from the legacy world to this new generation architecture. After this migration, the final step would be to destroy the old-fashioned technology. In the step mentioned before of combining both architectures, it's mandatory to provide a publishing layer of APIs and services to redirect from channels to both backends, the legacy one and the next generation one. So this access layer was where the customers comes from, and it's called channels. These channels could be the branch offices, ATMs, mobile apps, etc. These APIs and services are based on microservices running on our Openshift deployments. And now I'm going to hand over to my colleague Carlos to continue with the presentation, explaining in more in detail these parts.
Okay, as a first step, we decided to go from a monolithic architecture to an architecture based on microservices. I'm not going to go into detail of how a microservice architecture works, but I'm going to give you a brief description of how we have oriented it. We decided to use all services that we deploy inside using gRPC communications. On one hand, we have what we call front services or channel services. These services receive requests from outside world via HTTP. Okay, we have HTTP connection inside the cluster, and then all connections inside the clusters go through gRPC. These requests can come from traditional applications, I mean, maybe the web or the mobile application, ATMs or branches, or even from events or batch processes. Front-end services call backend services using gRPC, as I told you before. In backend services, we do not have drivers for any database or host. For this, we have created specialized services which are consumed via gRPC and which allow you to run SQL queries on the databases or just to the mainframe via an API. We call this Titan, which are specialized services. Those are programmed by us. And we get rid of the drivers or even the queues from the services. Thus, microservices consumes API and you don't need to have specific drivers from any provider, and you don't have to update them. Just you can run queries just via an API. Now we're going to see an approximation of how we have implemented this architecture using Kubernetes. In our case, we don't use Kubernetes, we use Openshift, but we don't use any strange feature from Openshift. We use just plain Kubernetes. And how we install all the modules that we need to maintain the same versions of all the components. Because you have to think that we have more than 24 clusters, Kubernetes clusters, with different versions, and we need to have the same versions of everything that we install all over the platform. So we have Openshift installed over OpenStack. We have all the Red Hat stack. Okay. So each one has an SDN. In the Red Hat reference architecture, the pieces that route the traffic inside are HA proxies, but we have replaced them with envoys because HA proxy in version 1 did not support gRPC, and we need gRPC support, as I told you before. This envoys allows us to hide our internal cluster architecture. I mean, we can have as many clusters as we want and reorganize them. All the deployments that we have within them, as we see fit all times. We have changed the architecture that we have inside, the number of clusters. Now we have clusters separating different charges that we have. We have clusters for the batch environment, we have clusters for the new online environment, and we have clusters for all the other stuff that we have. As in other time, we have clusters separating countries, because in the bank we have several countries. In this architecture, we are running Spain, and we are running services from Spain, from what we call global corporate investment banking, Mexico, Colombia, Peru, and Argentina. So our first approach was to have clusters divided by countries, and then we changed and divided it by functionality. As we have the envoys, we can put the traffic to the services, and nobody knows how we are dividing our cluster. You know. The symbols also allow us to update the platform. We can do blue-green from platform deployments. If we need to update an Openshift, we can deploy an Openshift just by the order. Then we move the services, we check everything is running okay, and then we change the traffic into the new deployment. For us, it's easier now with Openshift full versions. They have choreos inside, and it's easier to do a migration. But until now, we are doing this. We have been doing this for years, and we are more comfortable doing platform blue-green deployments than updating the production clusters. So why do we have so many Kubernetes installations? Well, first of all, we have what we call development environments, which have tenants where we deploy just to develop for us as a team, where we develop new features and where we try new versions of every component that we install. We also have what we call play tenants. Play tenants are tenants that we use for integrate with other platforms, other deployment platforms in the bank. I mean, when we test installation, where we test the integration with the log system or the alerting system or all the systems that we have in the bank. And we also have what we call work and live tenants. For us, work tenants are the previous environments for our developers. So the development environment for the developers in the bank is in what we call work tenant. They have 4 virtual environments. I mean, development, integration, Q&A, and also the quality team of the bank just to test the software. And we have what we call live tenants. In those live tenants, we have the production services. We also have what we call a platform tenant. What we have in platform tenants, an application that we will call App Engine. What is for us App Engine? App Engine for us is an API that we have built internally. It has trust from the technology that we use inside. It knows if we are using Kubernetes or we are using Istio or everything we have. It just make a deployment and can give it and can set traffic into that deployment. You can do blue-greens and you can do everything just with a you know. For us, it's very important because we have changed many times pieces inside the platform. We used Linkerd for a very long time, and then we decide to replace it with Istio, and nobody knows it. Just we replace the piece, and that App Engine has all the changes just to make it run with any of our customers know that they are running with a different service mesh, you know. This is placed in his own tenant, in his platform tenant, just to make it more reliable, you know. And we have replicated this typology of tenants in both data centers that we have. We have in the bank 2 main data centers. One is here in Madrid and the other is in Mexico City. Madrid gives service to the Spanish bank and to global services and also to corporate investment banking. And Mexico gives service to all banks we have in America. We have several banks. I mean, Mexico, Colombia, Peru, Argentina. It was the United States, but we sold them a couple months ago. And also, I mean, Uruguay, and I don't know if we have minor regions, but we have cloned the deployments that we have in both sides of the in both data centers. You know, well, as a platform, in addition to allowing containers to be deployed, we offer the following functionalities. We send logs to the bank systems. Today, we are forwarding logs to 3 different sites. We have the bank legacy work system. We have a brand new log system that we are developing. And also we have the typical audit system that you have in all the banks, you know. On the other hand, we as a platform must monitor the consumption and alert in case of infrastructure problems. So we are deploying also a monitor and alerting system. And for this reason, we don't install only Openshift. We install many more components, and we must maintain them in the same versions for all the components that we install. In all the cluster of the installation, both in the Madrid and Mexico data centers, we must have the same versions of everything that we install. For this, we have assembled what we call systems and modules. A system for us is a generic. It shouldn't know anything about technology, and it can include one or several modules. I mean, for example, log system. All the systems that we have are versioned. You know, we have installed the log system in version 1.4, and you know that system inside has the linked in a fixed version, and also the aggregators in another fixed version, and the Elasticsearch with a fixed version. We don't have installations connected to internet. We made all the installations that we have connected to an internal Artifactory. So we are sure that everything we install is in the version that we say. Even with the operators, you know, when we install an operator, we open the code of the operator and we tell the operator to go to an internal Artifactory and download all the versions from fixed version, because we had several problems with operators. If they go to the internet to search for versions, and every time you install the operator, get a different version. It has lots of dependencies, and all the time that we did this, it was impossible to install the same version of an operator into different. I think the last time I counted them, there were 24 Openshift installations. So we modify the operators and we make it install from the internal Artifactory. And for us, a module is just a way to install a particular technology in an instance. It belongs to a system. I mean, for example, we have the module Kibana or the module TD agent with a version. So the system has a collection of modules, and we have a list of everything we installed in each tenant that we install. You know, what systems do we have? We have what we call base infra and state manager system. It's just install the networking and everything that we need. Then we installed, it has a bind DNS module. It gets the state manager module. The state manager, what we call the state manager module, is just a key value database where we write every installation that we have done in the bank. So for us, it's like a central repository where we can see all the tenants that we have, which version of each system has installed, you know? It's like the brain of the installation. Then we have what we call Sebastian Medal. Sebastian is the internal piece of the bank, security piece that we use to, is a bastion, you know. We also installed the basic network model, which defines the networks that we have, one public and one private. The gateway system, where we installed Istio and all the configurations that we need. And we also have the log system. Log system installs a typical FluentD installation in high availability. Just as said in FluentD documentations, we are not doing nothing strange, you know, just the aggregators and the FluentD. And the only thing strange that we have is in the aggregators, we have installed 3 different Ruby gems just to send the logs and process the logs to 3 different systems, you know. We also install an Elasticsearch just for, it's deprecated. We use it to make a brief diagnostic when we have any problem. And we also have the monitoring and alerting system. With the monitoring and alerting system, we install an overlay Prometheus just to alert everything, which is alert manager and everything, all the configurations. And we made HA deployments of Prometheus just in bare metal, you know, in VMs. We don't make Prometheus in pods. They are outside of the cluster. We also have what we call the execution cluster system, which installs Openshift. Nowadays, we are installing Openshift 4.5. And that's all. I'm going to hand over to Cesar to continue with the presentation.
Yeah, thank you, Carlos. Now we are going to see the challenges in our department, the challenges we have in our department. So, as said before, our Openshift on-prem is running over the VMs provided by OpenStack. This stack nowadays implies to handle 2 SDNs, the OpenStack SDN and the Openshift SDN. So we are evaluating pros and cons to decide what's the leanest architecture, offering the capabilities to deploy these blue-green deployments that Carlos was explaining. We have some clusters that have to deal with heavy workloads, like the ones dedicated to batch processing, for instance. As the infrastructure is finite, sometimes we have to find a way to prioritize some of that deployments over others that comes before, and without killing the other ones, just pausing them. Another, obviously, not all the end-to-end of the flow of one application resides inside the same Kubernetes clusters. The databases, for instance, are living outside the cluster. And for that, it's a challenge to avoid bottlenecks of the egress pods. Another example could be if we have the backend of the application on-prem and we want to extend it to the public cloud or between the clusters in the same data center. So trying to extend the cluster between on-prem and another cluster or towards the cloud for the service mesh, in our case Istio, and for the SDN is another challenge because of the orchestration of this service mesh. So it's crucial to have the proper monitoring tool, as Carlos was mentioned before in the previous slides, not only for the infrastructure, but also for the applications running over it. There are some tools that better fix up for some demands, like FluentD, explaining before. But there are some other issues not solved with that option. For batch processing, for instance, we are dealing with Spark workloads that requires a kind of streaming login. So for that purpose, we have over-the-table solutions like Kafka, for instance, to avoid losing any kind of these stream monitoring logs. With the current OpenStack deployment to provide the VMs to OpenShift, we are making the most of the host, avoiding pod limitation over bare metal options, for instance. But would it be a good idea to make the control plane of Kubernetes the standard for the infrastructure management, for instance? And not only that, are all the applications running to run over this new deployment? So this is another big challenge we have facing because of the impact over the architecture we have in place. So bearing in mind the challenges mentioned before, the evolution of our infrastructure could be something like the one shown in the slide. A common Kubernetes layer to offer different flavors to the different apps requirements, like PMs for databases, PNs and pods for the management of our Kubernetes or for the legacy, and pods for the microservices clusters. And allowing as well the option to have a specialized hardware depending on demand of the applications. For instance, deployments that need the use of GPUs for the increased demand we have for the artificial intelligence in place. Making use of the APIs for the self-provisioning and managing the service resources like apps, endpoints, packets, streams, databases, including the roles and policies needed. So this new architecture would cause us to review and in some cases rethink some challenges that we have covered in the past. These ones could be related to the security stack, the observability tools, automation tools, to include more options, given the need of deploying the same code, whatever the cluster would be, in Europe or in America. Increased even more the skills of our engineers, avoiding the vendor locking and using the market-leading techs that will ease our evolution on-prem and in the public cloud. I would like to thank you for attending this session, and we are open to answer the questions that maybe some of you could have.
Cesar, Carlos, thank you very much. Do we have any questions for the BBVA team? Again, we'll be tracking additional questions in ScaleX Slack channel throughout the course of the day. And if we see any pop up there, we'll forward them on to the BBVA team and reply back in our Slack channel. Carlos, Cesar, thank you again for presenting again for a second time at ScaleX. We appreciate your time and your insight and your knowledge. Thank you and have a great rest of your day.
Thank you.
Thank you so much.